right, everyone can hear me better now? All right, I am Mike Buford. I'm the organizer for this meetup group and also director of engineering at greenhouse.io. Thank you to Squarespace for hosting us tonight. And first up, I'd just like to introduce John Colton. He is the CTO of Squarespace and has a few words for you, and then we'll get into the talks. Here you go.
Hey, Michael, thanks. Thanks a lot for bringing your meetup here. Just wanted to welcome everybody. If you didn't find it, the beer has been kind of hidden under that island in the back. A couple of guys pointing to beer. If you need drinks, if you want any other drinks that you don't see out, feel free to open that refrigerator and take anything you'd like. There might be a little bit of pizza left. I guess for the privilege of hosting the meetup, I get to do a plug for recruiting at Squarespace. So as Mike said, I run engineering here at Squarespace. We're doing a lot of exciting things. If you have any interest, please feel free to check out squarespace.com/careers and take a look at what's what. But otherwise, I'll get out of your way and let the meetup start. Thanks.
Thank you. All right, first up, we have Franklin Angulo. Hopefully I pronounced your last name properly. I did. All right, awesome. And talking about scalable monitoring and alerting at Squarespace. So here he is.
Hello. So my name is Franklin Angulo, and as they said, I'm a software engineer here at Squarespace. I've been here for about a year now, and most of what I've done here is this, scalable monitoring and alerting. So today, what we wanted to share with you guys is the experience that we've had over the past couple of months building a monitoring system that scales well. It's based on Graphite. And Graphite doesn't have a real logo, so we just put the rock in there. And then we just surrounded it with a bunch of tools that make the experience better. So we're going to share this with you now. So in the beginning, around September, I joined in August, and in September, I started code. So I was fixing bugs. I was developing new features as developers do. And we rely heavily on our friend Jenkins. So we do code, we make unit tests, we make integration tests, and we trust Jenkins to build our artifacts and generate the artifacts and run all of our tests. Once that is done, you move your artifacts to staging, and then to production, and everything is great. But I was accustomed to another step. Once everything's in staging and everything's in production, I want to figure out whether it's working correctly. Maybe it passed the tests, everything's fine, but as soon as it hits production, it blows up. And I want to know when that happens. So that's the extra step that I needed that we did not have. If we combine those two, then I'm the happy guy at the end, where I just push a button in Jenkins and I see my graphs and I make sure everything is fine. So this is where I wanted to be. The other thing was that around the end of 2013, we got really popular. Word got out that we were going to launch an ad in the Super Bowl, so hackers would attack us every single day. Like in a given week, we would be attacked at least one day. And what I found is that along with the systems team and our server team, we were looking at so many dashboards all over the place. So there were the S5 dashboards, cacti graphs, pingdom graphs, boundary, Prolexig, Observium, and Mongo graphs. All different tools that you need to know how to log into. They look different. They have different thresholds. And it was a real pain to collaborate with everyone to figure out what the issue was. So we established the vision. Everything has to be published with ease. So if a developer wants metrics about their new feature, he should be able to publish that to Graphite easily. Systems teams want CPU usage, memory usage, easily published into Graphite. And the second point, Graphite would be the single source of truth. So Pingdom might be there, cacti graphs might be there, whatever else might be there, but everything ends up in Graphite, and that will be the source of truth for everything. And the third point is that we wanted to democratize the access. So engineers are really good at publishing metrics, but they're not good at making visualizations of them. So what we found sometimes is that engineers would publish the metrics, and then a designer would build a dashboard out of those metrics, and it was really good. You could actually understand what was going on. So everybody should have access, no logins, all internal, but everybody, no matter if you were not an engineer, you would have access to it. So in September of 2013, this is how our setup looked. Just a show of hands, how many people have used Graphite before? Cool. How many have used Graphite with Whisper? Other than Whisper? What? Redis? Redis. Okay, so this is how our setup looked. We had one aggregator, one cache, writing through Whisper to the file system, which was on rotating disks. And then there was a single Graphite web app to show the dashboards. This worked well until people started publishing more and more and more, and then it gave up. In January, before the Super Bowl, this is how our setup looked. So it's kind of the same, 3 different servers, each running 16 relays at the top, talking to 10 caches in the middle layer, and then each one separately storing to the file system on rotating disks through Whisper. Now, if you notice, there are 3 different web apps. And in order to do this, you have to implement something called federated storage, which just means that each of the web apps talks to each other to figure out where the metric is. So if a user comes and opens a dashboard here, but the metric is in the file system over there, the web apps will communicate and figure out that and render the graph. So this is how it looked like before the Super Bowl, and it was great. Like the graphs would load fast, a bunch of metrics were getting published, and we had many, many dashboards because we wanted to feel confident coming into the Super Bowl that we knew what was going on. So this led to a change in culture. So people would talk in terms of graphs. Before this, people would say, oh, there's a latency spike, but people either didn't trust the graphs or just weren't accustomed to looking at them all of the time. We use HipChat for internal communications. And as you can see, this is an example how people started talking through graphs. If you would say there's a spike in P95s, people will ask for the graphs. And then at a later point, people just would paste them there. This was really cool because as an additional thing, there were many parts of the system that we did not know what was going on. So we were blind to it. And then engineers were happy because they were blind, now they could see. And this led to a lot of emotion and people expressing it, like in this case. And it was really nice to see because you provide the metrics to people and they're happy because they understand what is going on. So the Super Bowl came and we thought we were ready, at least from a monitoring perspective, right? We thought, oh, this is great because we will see what is going on as the ad rolls out. That's what I thought, at least. But that's not what happened. Graphite got so popular that, okay, the engineers looked at it, but the marketing people were looking at it, business people were looking at it, everybody was looking at it, and it crashed the little thing. So if you were an engineer minutes before the Super Bowl and you loaded a graph, it would take like 5 minutes to load. It would load eventually, but it would take 5 minutes to load. By the time it loaded, it was useless. So minutes before the Super Bowl, I had to change the ports of everything to restrict access only for the people that really mattered. So this was terrible from my perspective, and I felt like this little guy. So what were the problems during Super Bowl? Reads obviously didn't scale. So even though the graphs loaded slowly, writes were flowing in perfectly. So it was the reads that were the problem. Second problem is I didn't know how my users were using the Graphite cluster. And the third point is that the dashboards are dumb in the Graphite web app. So if you say, in a simple example, you want to load the past 30 minutes of latencies of your server, it will go and grab the 30 minutes of data from Graphite, bring them to the browser and render them. And then it updates after 1 minute, and it will go get the exact same 30 minutes plus the extra minute that it was waiting for and render it again. Why not go only to the server for the last minute? You already have the other 29 minutes. So this is why it was dumb while rendering the graphs. So I set out to fix all of these issues. So first issue, reading. We changed the file system to solid state disks. A single server just as a proof of concept to make sure that it worked. And it did work for a while until people started to use the dashboards really like a lot. And this guy would die. The web app would just crap out. So as a side project, we were also looking at other open source projects related to Graphite. And one of them is the Graphite API. It takes the Graphite web app, strips all the dashboarding tools and everything, and leaves only the API, which is really the greatest thing about Graphite. And it's called Graphite API. So we plugged that in where the web app used to be. The main difference between the Graphite API is that it doesn't talk to the caches anymore. It goes directly to the file system. So if you want to make use of the caching of the Carbon caches, you don't have that anymore. But in our case, we were okay with that. Then this last month, we reintroduced. So since the Graphite API fixed all of our issues, dashboards are loading blazingly fast. Everything looked fine, so we reintroduced the aggregators. An aggregator just says, for example, if I have 50 servers reporting their P95 latencies, and I'm just interested in the maximum of those P95 latencies, I can do an aggregation over the 50 servers that gives me a single metric of the maximum. And this makes querying a maximum dashboard graph, a maximum latency graph, really cheap because it's a single metric compared to 50 metrics running a maximum function on them. So we reintroduced the aggregators, and this is how our setup looked today. A single server with SSDs using Graphite API and a stack of 8 relays, 10 aggregators, and 10 caches. Why do we have this here? The relays are really CPU intensive. So we need to split them out so that our CPUs aren't at 100% all the time. And our aggregators are memory. They consume a lot of memory. So if you think about it, if I report metrics every 10 seconds and my aggregation is every minute, I have to keep in memory 6 data points for every metric there so that I can compute the functions. So that it works, we have to split it out like that. My second problem was I didn't know how people would use Graphite, and I really wanted to know. Since we were using Graphite API, we modified the source code. We added log lines that would tell us the query range and the query pattern and spit it out to a log. We would grab it using Logstash, index it into Elasticsearch, and build a dashboard using Kibana, which really looks similar to another tool that I look at later called Grafana. And we ended up with a dashboard. So at any point of the day, you can figure out how people are using Graphite. What we found is that if you can see in the pie chart, most of our dashboards are being queried for the past hour. But at certain points of the day, if you see the little yellow lines there, people query the past 30 minutes. And if you can see the purple line is for people making queries of the past 7 days. So this is really cool information. Not that I can do a lot with it, but at some point we might want to enhance functionality somehow. The third thing we needed to fix was the dumb dashboards. So there's a tool called Grafana. Anybody know about it or used it? It's supposedly more intelligent when rendering graphs, but also it's much, much easier to build graphs in this compared to the Graphite web app. And users love it. Before in the Graphite web app, I have to build tutorials to teach people how to use the web app. Here is intuitive. I don't have to teach people how to do anything. Now, So we're monitoring stuff. I can see a bunch of dashboards all over the place. And I love looking at dashboards. But at some point, I have to sleep. And I need a computer to look at the dashboards for me. For this, we have alerting. In the Grafana tool, we can have a dashboard with a metric and specify thresholds for it, warning and critical thresholds. In this case, we set a threshold at 0.5 seconds and 0.7 seconds for critical alarming. This is cool because you can visually see whether something's going wrong, but not when you're sleeping. So we built a little script that would query Graphite with our parameters. In that case, the warning levels, the critical levels, how many data points you want to read, and tell you whether something was in an alert level. So this is an example. Let's say that the little red dots are your graph or your data points. And in the script, you can say, I want to read the past 30 data points, alarm if at least 9 of them are above critical or warning thresholds. And then we have an additional parameter to skip anything in the tail, because sometimes Graphite has lags, so you need to eliminate those. Most of our metrics are published every 10 seconds, so this means that I'm going to skip the past 15 seconds. I'm going to read 5 minutes of data and alarm if data points are above the thresholds for 1.5 minutes. Now it's cool, we have the script. Now how do we use it? So we integrated the script with Nagios, and you build these little snippets with a title, a link to some playbook, or something that tells the engineer what to do if he gets this alarm. And then you do this check command that just says, go and check Graphite with the given parameters and tell me whether something is alerting. If something is alerting, the appropriate person will be either emailed, paged, or text, whatever. So this was really cool, the integration with Nagios, so that when you're not looking at the dashboards, you would get the alerts. Now, we're nowhere near done. We have the following next steps. We would like to have replication, scale even more, and our alerting should be a little more intelligent and robust. So by replication, I mean, first, what we would like is that everything would fit in a single machine, so we don't have those outliers there. Once we do that, we would like to have complete replication. In case one of the servers dies, we still have the other one. So we want to get to that point. And then for alerting logic, we need something more intelligent. So I'll give you 2 examples. When one of our customers goes to Shark Tank, we get a spike in number of visits for their site, which is really cool because they're using a Squarespace website. If you look at the number of requests per host, you would see the spike. And since more requests are coming in, probably the number of active requests per host, or the number of requests the host is actually working on at this point, will also spike. That doesn't mean that there's a problem, right? Maybe you're getting DDoS attacked, or maybe it's just organic traffic like Shark Tank. So that's not really an alert. Nobody should be woken up because of that. However, if one of our teenage sensations tweets about some form that girls need to fill out to get their merchandise, we will see something like this. So form submissions for Google spike crazily. Now this is okay as long as Google doesn't throttle us, because what happens is that the active requests at our servers keep waiting for Google to approve our requests. And if you combine this one with this one, then you get an alarm saying Google is throttling us. So then somebody needs to be woken up. But if only this one is alarming, but not that one, it's not a problem. And if only that one is alarming, but not this one, it's not a problem. So we need a combination of both. So we need something like, alerting logic. You can say this one and this one. Where we have 3 different things, 3 conditions, You can do A or B or C. So we need something like that. If anybody has used Stackdriver, they have this functionality. If anybody has been at Amazon, they have Amazon Carnival, which does exactly this. Another example is we might see a user metric, number of trial subscriptions, signups dropping, and then we drill deeper and we say at an application level, the internal subscription API calls are dropping, and then we go drill down even more and we see that the database host is offline, and therefore that is the root cause of the problem. We shouldn't alarm on the top one. Now, this is only like 20 minutes of talking about Graphite. If you want to learn how to use Carbon, how to use Whisper, how they work together, how you scale installations, you can visit my blog and you will find complete details about how to do this. Because it takes a lot of time, months. And I'll open it up for questions.
How did you settle on 10 seconds?
It was legacy. So most of the 10-second ones are quota hail metrics from our Java application. And it was set like that. At some point, we thought maybe we'll move it to 30 seconds or 1 minute, but we didn't like that. We want like something granular like that. But we also didn't want to move it to 1 second because it's just way too much. We thought 10 seconds was a good trade-off, not 1 minute, where by the minute, by when you get the metric, maybe you have nothing to do, and not 1 second when it's just way too much information. We're not like financial data or anything like that. So 10 seconds was okay. Yeah.
Did you consider any service platforms to do this instead, or you did buy it?
Yeah. So there's a company that does this as a service, like hosted Graphite, but we didn't want to release control. So like the dashboards run by Graphite it's their business, right? So if for some reason hosted Graphite dies, we are blind. We don't know what's going on. So we wanted to keep this close to us and supported by us so that we can do whatever we want with it. And also if something happens, it's our responsibility. We don't have to wait for other people.
Have you mentioned any sort of responsive auto-scaling events happening, self-healing based on common problems, anything like that? Well, you can see in learning that problems happening.
Yeah.
You have scripts that automatically respond appropriately. So sysadmin is probably going to do kind of the same thing on the same class of problem over and over.
Yeah.
Do you have to wake them up before in the morning, or do you just invoke some shell script somewhere?
Yeah, we're not there yet. What we do have is the debate of whether the engineer should be woken up or not. So if we have hundreds of servers and one of them spikes up, like who cares, right? It's just one server. Let the engineer sleep and he can figure out in the morning. But if it's 10% of your fleet that's having issues, then somebody needs to be woken up. We don't have the hook to restart servers or whatever automatically yet. And I don't think we would do that because as an engineer, I want to know why the latency spiked up. So like we have engineers that restart servers without understanding the root cause. I am of the opinion that I want to know what caused that latency before the server is restarted, right? Even at 3 in the morning, yeah? Any other questions? Everything that we serve is located here, even though we have customers in most all the countries in the world. Cool. So who's next?
Thank you so much.
Thank you, Franklin. Who wants to go next? Is it Sean or is it Tyler? I usually coordinate that in advance and didn't this time, but Tyler says Sean, so Sean, you're up. I'm getting lazier about these as time goes on. Apologies. And by a show of boos, how upset would people be if I didn't do this next month but picked it back up in August? Okay, good. July, I'm taking off.
Nice. Cool. Oh, that's a fun game. All right, so we had some fun AV games. So we're going off a PDF, so some of these will be a little weird, but should still be good. Oh, well, that's fun. Are you guys hearing a weird loopback up there? Or I guess something about the here, you got a weird echo. Anyway, so hi, I'm Sean. I work at Bitly. Real quick before we dive into stuff. Oh, that's a fun game. There we go. Cool. So pretty much anytime I give a talk, I get a pretty immediate reaction of Bitly. Really, how hard could that stuff be? It gets a little ridiculous. In the actual slides, these are animated GIFs. So, right, this stuff's child's play. I can make a URL shortener before you're done writing, giving this talk. How can this possibly be interesting? If I grant doing that at a large scale and in a highly available way is interesting, how on earth do you make money with that, right? Nobody's going to pay for that. For us is branding. So most custom short domains you see are run by us, and people pay us for that. And analytics. So we have a few hundred brands and publishers who pay us to help them understand what people are paying attention to on the web. For context, to kind of the scale of the problems we're dealing with, each day we see about 200 million redirects. That's actually somewhat outdated. It's a bit more now. That works out to about 6 billion a month. Now I think it's almost 7.5. We see 20 million shortens, 4 million page crawls. And we do that with about 400 servers spread across 2 data centers with 25 engineers doing 20 plus deploys every day. So that's a lot of stuff going on. So this talk's going to focus on kind of what tools and practices we do to keep that much stuff going on and not go insane and break everything. And really, at the end of the day, it's about managing tension, right? So on one hand, again, the GIFs. Anyway, the dog's supposed to be fighting with the baby for the food. So on one hand, we want to, oh, come on. All right, on one hand, we want to be moving fast. Again, the subway train's supposed to be moving. Narrated GIFs, the new thing. Right, so we got to move fast, right? We're a startup. We have competitors. And we have our own needs, right? Like, we have a limited runway. We got to get stuff shipped out. On the other hand, what is going on? Here we go. This is the towers collapsing, and they go, oh, God. But on the other hand, if we break stuff, that's bad, right? Like a very non-trivial portion of the internet runs through our servers. And if our stuff breaks, people notice and get angry, and they're justified in doing so. So, and a lot of things you would do to move faster tend to make things break. So how do you kind of balance those tensions? There's a lot of how we do stuff, right? The biggest part of one of the big ways we do that is automation. Automate everything, right? I forget. It's also hard without presenter notes. Right, but so, if you're doing something once, fine, whatever. If you're doing it twice, write a bash script, right? Robots and computers are a lot better at doing things repeatably than humans are, right? And aside from that kind of reproducibility, they can also do it a lot faster, right? So I mentioned we had 400 servers. We have 4, maybe 5 ops people, right? If we tried to do everything manually, we would just break down crying every day. Right, because things break, right? That's also about half of those 400 servers are in EC2. And when you have that many servers in EC2, like we get 1 or 2 emails that a server's disappearing a week, and then 2 or 3 servers a month just flip out of existence. That's a thing, right? If we were manually reprovisioning those servers, that's an hour or a day of developer time every time one of those servers flipped out, right? So that's not going to work, right? You'd need an army of sysadmins to keep up with that. In addition to all the other stuff of spinning up new servers and dealing with patches and all that other stuff, right? And doing deployments. So automation is critical. Again, robots way faster than humans for well-defined tasks. And the reproducible, which is really powerful in that now I can have confidence in things that I tested, right? If I write a script and given the same inputs in the same environment, and I run it and it does something today, I can be really confident that it's going to do the same thing tomorrow. Developer, I could kind of have that faith, but they're humans, and well, things go wrong. Similarly, it makes review a lot more useful, right? Again, I can watch what somebody does today and review it and critique it and have an idea that they're going to do it the similar way tomorrow. But if I do that with a script, I know that, right? So it's really pretty important. Similarly, they're all a lot better at watching things, right? So this is Jenkins. So we have it run our tests on every single open pull request that has code pushed to it, right? While we aspire as developers to run the code against every commit we make, relying on them to do that's not necessarily going to happen. But Jenkins will do it every single time and will yell at you when things break. Useful. Let's see. So the next kind of major area, this is just going to be a shotgun of stuff. So definitely feel free to ask me questions as we get to the end. State management, right? So Bitly's been around for about 6 years, and that means there's a ton of code. And so when I was interviewing at Bitly about 6 years ago, not 6 years, a year and a half ago, excuse me, we were talking about how they manage code and as you do. And one of the things that came up is that for all the services, all the code we have, there is one monolithic repo, right? And at first I was like, what? That is crazy pants. How does that not become a wild rat's nest of mess that you manage? And when we talked about it a little bit, I actually kind of came to appreciate kind of what was going on there, right? So if you're not careful, that kind of approach can lead to a crazy rat's nest. But if you have some discipline, have a review process, and have some conventions about how you organize things, you can manage that chaos. And you get this really nice benefit of now you have a complete snapshot of your entire system minus data, right? So when we check out a commit from our repo, that gives us all the code on all the servers, plus all the configuration for all the services that those run on. Makes it really easy for us to do rollbacks, right? If everything's on fire and we need to roll back, we just need to find a commit instead of 6 commits, which can be really powerful. Right, so you just have the configuration and that code are joined in a really strong way, which is powerful. Excuse me. Additionally, if you're doing any kind of forensics or if you're looking to understand the history of a project, having that joined state is, again, really useful because you get discrete working pieces at each commit. So you can look back and see how that progression worked, and it's much easier when you have kind of those complete pictures at each step. Next huge fundamental part of how we do everything is service-oriented architecture. This is a Lego, it's like a recursive Lego thing. So at Bitly, there is no one monolithic app that does everything. There's dozens of little services that all talk to each other and snap together in interesting ways. And that has a ton of useful benefits for us. One of the biggest ones for us is what failure looks like, right? It's almost impossible for all of Bitly to go down, right? Obviously, our data center can get knocked off the internet. That has and will happen again. But even then, if you're spread across multiple data centers, what failure ends up looking like is loss of functionality as opposed to just going dark, right? So if our analytics system is having some really catastrophic issue, that's unfortunate, and people are not going to be happy, including ourselves. But redirects are unaffected, right? They're still running just fine. Additionally, it means that deploys are a lot easier, right? So when I said we're deploying 20 plus times a day, we're not deploying to 400 servers 20 times a day, right? We're only deploying to the particular servers that change effects. So most deploys only touch, 5, 6 servers at most, 30, right? So again, it minimizes the impact that any one deploy is doing, which then lets us move fast and not break things. It also makes it a lot easier to understand everything, right? When you have everything broken down into these services, your infrastructure and your system from an architectural standpoint starts looking like your code, right? So just like functions and classes allow you to either focus on the big picture and see how things interconnect, or inverse those API boundaries and just look at the implementation of a given thing. And just kind of have those bits and pieces in your head at one time. Breaking everything up into services that have defined boundaries gives you that same benefit of abstraction, which is really powerful because, again, 6 years worth of stuff. I've been there a year and a half. There's still stuff running that I don't fully understand. And that's okay, because if it starts breaking, I can dig into that one piece and understand that. It's also really nice in that it lets you use the right tool for the right job. So by default, typically we use Python. In places where we need to do things fast or have crazy concurrency, we use Go, we use Java for search stuff, right tool for the right job. And since it's all just asynchronous queues and HTTP, gluing everything together, it's okay. We can change platforms, no problem. Similarly, we can adjust hardware as needed, right? Kind of our default at this point is like a C3 large and EC2, right? Good, medium-sized box, fast, decent amount of RAM. But if we are doing something, again, like search, where all the RAM is a good thing, we can use a box like that. Or if we need a box which is a ton of storage or spinning disks, we can just do that and tailor things as needed, which in turn, and we can also scale things as needed, right? So if any one cluster needs more capacity, we can just add capacity to that cluster and nothing else has to care about it. By doing all this tailoring, we can save a ton of money, right? We don't have a whole bunch of hardware sitting around not doing anything, or have to over provision things just for this one thing that might happen once in a while, which is, again, very useful when you have a limited runway. Next bit on how we do things, and this is kind of just a design philosophy. Async is better than sync, except when it isn't. And here I'm not talking about like, Node or Tornado or whatever, but at like a system level. And particularly thinking about how you design those services to communicate, how pieces fit together. Ideally, things should look like letters in the mail or email, as opposed to two people having a conversation, right? And the reason for this is it gives you much better isolation between things, right? If Service A and Service B are talking to each other and Service B has an issue, if it looks like two things having a conversation, Service A has to sit around and wait until Service B comes back. But if it's asynchronous, it's okay because things can just pile up between them. And when Service B gets back, it can work through the backlog and everybody's happy. Additionally, it gives you looser coupling, right? Especially if you design things where you're saying, describing things as events instead of commands, saying this happened instead of go do this. It makes it so that Service A doesn't have to know anything about what Service B is doing. It doesn't have to care, it doesn't need to know, which makes it super easy to change out implementations or introduce new things that consume a given stream. Again, easier to have isolated services, easier to understand, easier to build complex things made out of simple components, which in turn gives you flexibility, right? So if you have all these Lego pieces and it's easy just to add in another one that consumes another data stream, or we've done stuff where like we wanted to change out the database, like the actual persistence system for a given system. So what we can do is just have the writes in one system going through our asynchronous queues. It's a pub sub kind of setup. Set up a new system with a new subscription to the same topic, pause that, let it pile up writes, build in, do whatever data migration we need to do, unpause the channel, resume the writes, and now just shift over the reads as we want. So we just completely changed out database systems without taking any kind of downtime, without doing that much more work. So it can be really powerful. It lets you deal with kind of congestion issues, right? If you have really bursty stuff that can take some latency, it's okay. Because again, stuff can pile up for a while, and then when that burst passes, you can just churn through it and you're good. The one place where this is hard, right, I said async is better than sync except when it's not, is when you really care about consistency and a little bit latency. And the reason for that is basically if you have to do like round trip messaging and really care about that consistency, you ultimately basically end up re-implementing TCP on top of TCP, which will make you crazy. And so examples of kind of uses of this kind of different breakdown. When you plug in a link to Bitly to shorten, everything that happens between you hitting shorten on that and then getting back a short URL is synchronous. The reason for that is A, we care about that happening really fast, and B, we need to make sure that's consistent, right? We can't give you the same short URLs we give somebody else that's crossing the streams. It's not good. But also, we much rather give you an error than give you a URL that doesn't work, right? So their consistency is really important. Metrics incrementing, on the other hand, if things are delayed a bit or off a little bit, we don't care. But if our metric system goes down and takes redirecting with it, that is not okay, right? So that's completely asynchronous to the point where like we'll give you the HTTP response and then put something on the queue, right? We're as asynchronous as possible there. Real quick hint, a lot of how we do this is this thing called NSQ. It's this awesome system we've open sourced. It's distributed real-time messaging. What does that mean? I'm actually going to skip through some of the details on this just because this talk was designed to be a bit longer. If you're interested, come talk to me afterwards or check it out on GitHub. Yay. One of the last bits, UIs are really powerful and interesting. Actually ties really well into the last talk, right? UIs make things easy and they make things it's important to make things easy, accessible, and timely, right? So the example of our deploy UI, it's basically just a wrapper around. Imagine Chef or Puppet, it's a crazy homegrown thing, close enough. But it tells you a bunch of really important stuff at the right time, and it's easy to use, right? If you're a developer and you want to deploy something, you say what servers, what code, give a comment, go. Done, easy. And you can see what's been deployed recently. So if you're a developer and you're deploying to the set of boxes that just got deployed to, you should probably talk to the person who just deployed there because you're probably going to step on each other's toes. Similarly, if you're on ops and you just got woken up at 4 o'clock in the morning and you see something just got deployed, A, you should ask somebody why they're deploying at 4 o'clock in the morning. B, it's probably a good hint of why things broke. Right information at the right time. At the end of the day, it's just a wrapper around a fab script. And again, kind of accessibility. Some people rather use a web UI. Some people use a command line client. Good. I have no idea how I'm doing on time, so feel free to just tell me to wrap it up at some point. Cool. NSQ comes with a really nice admin interface. Again, right information at the right time, so you can kind of see where stuff's getting published, where it's getting consumed. If any of these lines are going up and to the right, it's almost certainly a problem. And then additionally, you can get some tools that kind of gets overrun by that thing on the side. But you can pause topics, you can pause messages, you can clear things out. Right information, right time, right tools. We do peer review, so everything goes through GitHub pull requests for us. We do this thing I really like where the only actual rule is whoever wrote the code can't hit the merge button, which then has a bunch of practices that fall out of that as far as how we actually do stuff. And additionally, aside from just reviewing the code, we'll actually write out checklists for deployment and validation if it's anything more than just deploy this box and go. And therefore, whoever's doing the review is both reviewing the code as well as the process for shipping the code and making sure we didn't break things. And these are open to everybody in the company. So a lot of times, even though the code I write might be primarily reviewed by one of the guys on my team, the ops and infrastructure folks can look at it and say, oh, hey, if you do that in that order, this will break, so maybe change that around. Oh, and we also integrate with Jenkins. So if things break in our builds, it's very obvious here, and if you hit the merge button when it says stuff's broken, we should talk about that. Excuse me. Additionally, by having all these pieces put together, we can roll out new interfaces as we need them pretty fast. This is called our red button UI. So much like our friends here at Squarespace, we got hit with a lot of DDoS attacks this last year. And in dealing with the responses to that, we found that we have like a failover plan where basically we can move redirects from our primary data center in Delaware to EC2. And we found that while the process to do that isn't overly involved, it wasn't completely just push a button and go. It turns out engineers at 4 o'clock in the morning who get paged are not the sharpest knife in the drawer. So it took them a while to like dig up the docs and actually go through the process. So we built this UI that makes it very easy to see, okay, decodes are at 0, so something's clearly broken. And stuff's apparently pointing in Delaware, so push this button, push things over, you're good. We were able to build this in like 2 days, just cobbling together our existing automation and graphite. Peer review, kind of talked about that already. And kind of related to that, we do a lot of work to kind of do architecture and planning up front, right? And we try and do that in a fairly lightweight way. So, right, and we're certainly not going through like checklist binders that are this big, right? But whenever we go to build something new, before we actually write any code, we just say like, okay, let's stop. Let's have a conversation and talk about how we're going to deal with a few things real quick, right? So how are we going to deal with migrations, right? So one of the things that we deal with is when you have more than one server, there's no such thing as an instantaneous deploy. There will always be the old and the new version of the code coexisting for some period of time. So how are the old and the new things going to communicate and interact? What does failure look like? How are we going to deal with that? Do we need to have things be able to route around failure? How are we going to deal with the loss of a host? How are we going to know something is broken, right? Again, 400 servers, something can break and you not notice it, real easy. We basically say if there isn't an Nagios check for something, it is broken and you just don't know about it yet. Similarly, once I know something's broken, how am I going to understand what's about it's broken? Why is it broken? How do I fix it? What logging is needed? What graphite checks are needed? And what else? I think this was about capacity planning. Oh, here we go. Capacity planning. Right, just going through a series of questions to ask ourselves, what is this going to need and what can we do up front to address this, right? If I know that a system's going to have really wildly fluctuating capacity, I can take different approaches in how I address a problem. That'll make it easier to deal with that than otherwise. But if I do that at the end of the process, that's going to be a much harder thing to address. One of the tools that we have to help dealing with errors in capacity is this thing called host pool. You can kind of think of it as a in-client load balancer. Should talk about that. And I forgot at this point. Cool, monitoring. So kind of as I touched on there, this is the stuff that will keep you up at night, literally. Again, automate all the things. If it's not automated, it's probably not actually useful monitoring. We use graphite a ton. Actually really interested in looking into that Graphena because this UI is awful. We build a bunch of kind of custom stuff on top of it. So this is like our overall API metrics. Again, any of these going up and to the right is probably a problem. And obviously, they're not going to tell you what exactly is broken or how, but it'll tell you that something is broken. Centralized logging and UIs around that's really powerful. Right now, we use this thing. It's kind of just a homegrown wraparound grep and syslog, but gets the job done. Eventually, we're probably going to move to Logstash and Kibana. This is really powerful because we have like 30 front-end servers, and a user's request might get sprayed across those. And if you're seeing intermittent problems happening across them, trying to trace that going to each server and looking at the logs is probably not going to be terribly productive. But if you can search across all the logs from all your servers and go, oh, hey, this is happening every time this user enters this value, probably going to be a lot easier to fix. So some final thoughts. Use the right tool for the right job, I think. Not the presenter slides. Sorry about that. Anyway, regardless of what the slides are basically be deliberate in what you're doing. Think about something before you do it, and monitor everything. And real quick shameless plug, Bitly, we're hiring. We'd love to talk to you. And that's all I got. Thanks. If you want to, cool. Any questions, or also happy to chat about more specific stuff afterwards.
As a writer of a web application, you're thinking about going to a service-oriented or transforming into various asynchronous parts. What's the defining characteristic of something? When is it a good idea to go in that direction? When is it actually?
I'd say a lot of it basically comes down to latency and consistency, right? So if it's okay for something to have a few seconds before it changes, that's usually a good sign. Additionally, and similarly consistency, or like if it's okay that occasionally things are off for a little while or things are eventually consistent, it's probably a good sign. Something that we've learned that helps a lot dealing with that kind of stuff is the more you can describe things in ways where the data of your system is immutable, right? So you're basically describing things that happened and then doing work on top of that instead of kind of ongoing series of changes to the same things. That helps deal with a lot of that. But yeah, that's the latency and the consistency is usually the biggest thing. Sure. So for most of our systems, we actually run with a decent amount of overhead. On the flip side, we also generally have fairly even traffic curves. It's relatively rare that we have like really huge traffic spikes. I guess it comes down to like I said, we see a fairly high request volume, especially for a company of our size. Accordingly, any one customer is unlike even I forget you guys mentioned a celebrity tweets something. It might move the graph a little bit, but it's unlikely. But it's rare that we see stuff going so far off the charts. The only time where we've really had that is during DDoS attacks, and there it didn't even get to the point of hitting our servers. Like the worst DDoS attack I think we were seeing was like 65 gigabits per second coming in of just NTP flood, and we had 20 coming into the data center. So it had to be dealt with upstream anyway. But a lot of it also then comes down to like tooling. So the fact that, and the way we design systems. So we can, especially in EC2, we can spin up new servers. In EC2, we can spin up a new server in minutes. In our physical data center, we have a bunch of boxes sitting around that are idle just for that reason. And those we can probably spin up in about a day just because they're physical hardware, so it takes more time to install stuff. And yeah, just keeping an eye on stuff and doing capacity planning is a lot of it for us. It depends on what you're comparing it to. Comparing it to something like RabbitMQ or anything AMPQ based, the advantage is it's completely decentralized, so you don't have any kind of centralized broker, which can be a single point failure or a bottleneck. The drawback is there's no strong ordering. Generally strong ordering within distributed systems is really questionable. But there are some stuff like Kafka where you basically, there's some more minor trade-offs you can have, and I'd be happy to talk more about it later.
You mentioned that all of the code abilities.
Yep.
So, what are the negatives that you have found back in that?
You definitely need a certain degree of discipline to make sure that you maintain the organization within that. So for us, like everything that's a top level is basically a service, which is going to be running as a process. And we don't allow any like code sharing between those, right? Like if you're going to be sharing code across those, you write that as a library and that gets installed just like any other like third-party library. So you need a certain level of discipline to maintain that order. There's some stuff that we might do differently otherwise. Like we'll, before we merge something into master, we'll squash down all the developers' interstitial commits, just because otherwise the noise in the repo would be unmanageable. But overall, it's actually had, again, as long as you have that discipline, it hasn't had too many downsides for us. You have to be a little bit careful about what you commit into the repo, but that's probably true for any distributed version control system, just because otherwise the repo gets massive. But for us, I mean, it's like 6 years of history. It's maybe, I don't know, a few hundred megs. It's not too bad. Yeah, I'm guessing we're probably wrapping after this one, or?
You actually have a little bit of time.
Oh, cool. That's good.
Again, related to one repo.
Yep.
One repo, and you said like if you're there, how can you be sure that some commits that going to what they
Mm-hmm. For us, again, basically discipline, right? So a lot of it is personal responsibility. So developers almost universally are deploying their own code. So generally speaking, people are responsible enough to like not leave something half done and go home. I mean, we have had situations where somebody will like hit the deploy button and then hit the bar. But you know, then we have a conversation and that doesn't happen again. But a lot of it also is that peer review process, right? So if we do have a deploy where like system A and system B are interrelated and like the order of operations matters there, that's part of what gets reviewed in addition to the actual code changes. And that helps a lot there. We have had times where we like, oh, hey, if we actually do it the way we were originally planning on doing, we'd have an outage. And we shouldn't do that. But if we do it this other way, then it works out. Any other? Cool. Thanks.
Thanks very much. Sean. Thank you. Subbing at the last minute.
Yeah.
All right. Sean actually agreed to sub at the last minute, by the way, when one of our speakers canceled a few days ago. So he deserves an extra round of applause for last minute preparation. All right. Next up, we have Tyler McMullen. He is going to talk about fast distributed cache invalidation. And here you go. Here he is. CTO of Fastly. Awesome dude.
Thank you. All right, so no speaker notes. This is going to be tough. Actually, how do I get my things up there? What's this thing? What's that? Ah, got it. Nope. Oh, there we go. Hi, I'm Tyler McMullen. Thank you for coming to see me talk. So if you guys will indulge me for a moment, I have a brief rant about the term full stack. So for a long time, well, not for a long time, for a while, I actually referred to myself as a full stack engineer. The problem that I eventually ran into with the term is that I eventually realized just how deep the stack goes. Right? There was a time when I was like, all right, I do front end code and I do back end code and I do databases. All right, I'm a full stack engineer. But the actual stack goes so much deeper than that. You have the kernel. You have all the different components of the kernel. You have all the protocols that we use, SSL, HTTP, TCP, IP, Ethernet, right? Not many of us actually know how all of these different things work together. And so for a while then I was super anti full stack. I was no more full stack, so bad. However, then I realized there actually is a difference in some sets of engineers, some certain engineers. And what I've started referring to this as is kind of a willingness to dig. So instead of just going, well, I have this problem, but it appears to be below, at a layer of the stack below where I normally work. I guess I'll just hack around it. There's a certain set of engineers that will actually dig deeper and keep going and keep going and keep going until they actually find the problem and can fix it at the right place. And so that's what I've actually started referring to full stack as. It's this willingness to dig until you can solve the problem the right way. So rant over. Mild rant. So hi, again, I'm Tyler McMullen. I'm the CTO at Fastly, and I have the great privilege of getting to work with an excellent team of engineers who I actually consider to be all either full stack engineers or full stack engineers in training. And I know I had more to say around this time, but I have no speaker notes. Bummer. Oh, right. So credit where credit is due. The more technical bits of this talk actually come from an engineer at Fastly called Bruce Bang. Who wrote the system that I'm going to be talking about briefly. So thank you to Bruce Bang. Yeah, actually, most of it's just shamelessly ripped off. It's fine. So a lot of the material for this and some of these sources are actually available here, brucebang.com/bimodal. So again, thanks to Bruce. So I work at Fastly. Fastly is a content delivery network. Who here is actually familiar with content delivery networks? Most of the people. Awesome. Cool. So the whole point of the content delivery network is to cache things close to the users. So who would actually want to do that? Well, turns out a lot of people want to do that. Some of these people use Fastly just for normal static content caching. Some people use it for somewhat more complex things, load balancing, edge content modification, things like that. So speaker notes. So let's talk briefly about how a CDN actually works, just so that when I start talking about the cache invalidation stuff, it doesn't, it actually makes some sense here. So this is a map of our current POPs that we have across the world. So let's imagine we have a user here in Australia who wants to go to, say, The Guardian, right? So this user makes a request for The Guardian, and normally, maybe the Guardian's origin servers are over here in New York. Now, Normally, that request would have to go all the way across the world to New York. Maybe they have to do TCP negotiation. Maybe we have to do SSL negotiation. All right. So that's multiple round trips that it has to take. And also that line right there is the biggest lie on this graph. The actual path that packets take across the internet looks more like a child's scribble than anything resembling a straight line. So ignore that part. So the way a CDN helps is that if we have this user in Australia, they actually make this request. The Guardian is using Fastly. Instead, that user will send the request to our Sydney POP. If our Sydney POP doesn't actually have that content, it'll make the request back to the origin server over in New York, which will already be faster because we'll be maintaining connections all the way across the world to New York, so you don't have the TCP or SSL negotiation. So it gets it back, and then the next user that comes along in Australia will then get that same piece of content directly from the Sydney node without any sort of like cross the world round trip sort of thing going on. I have no idea what I was supposed to say on this slide. Right. Okay. So this is all fine. This all works fine, as long as the content that you're caching doesn't actually change very often, right? However, if it does change very often, then we start running into problems. And that problem is cache invalidation. And cache invalidation is one of these like big computer science problems that has actually been plaguing us for a long time. And so this is our stab at solving it in a distributed manner. Right. Yes, we know. Thank you. Cool. So why would someone want to use cache invalidation? So let's say, again, the Guardian, they decide, there's some big breaking news story, and the Guardian wants to update their homepage. Well, if that homepage is cached, then we have a problem, right? So we need to invalidate the cache of that homepage. Or if someone changes their avatar. So in this case, we need to invalidate all the pages that have that particular avatar on it. Or even DMCA violations. So being able to take those down rapidly is pretty important. So essentially, what cache invalidation in the CDN comes down to is really a messaging problem. We really just need to send a notification to all the different servers as quickly as possible. And so that's what we'll try to do. So there's a few different ways we can do this, and we've actually built several different versions of this system over the course of the last 3 years at Fastly. I'll go through like the first two really quickly before we get into the third one, and I'll probably go through that pretty quickly as well, and then you can ask questions. So the first approach that we took was a central service. This is actually a pretty easy one to build. We have some central service where if a user requests a piece of content to be purged, we send a message to the central service. The central service then coordinates with sending that out to all the different nodes around the world. And then the way that we ensure consistency in this case is that those nodes return an acknowledgement back to that central service. So there's this one particular service that knows the state of every node at every time. Oh, cool. Right. So the problem with a central service comes in when we have net splits. When there is some reason that a node can't communicate with some other node. So in this case, we lose that particular piece of content right there, which should be a GIF that is like exploding, but that's fine. Right. So central service has this like cool property in that it works and that it's simple. Like anyone can implement this and it's fine. The problems are that it's unreliable and it's high latency. So rather than taking advantage of locality of nodes with each other, we instead have to send all the messages down to one central node and let that then send those messages out across the entire world. So here's another idea. And this is kind of akin to the second version of the system that we built. All right, so what if cache servers can send the purges themselves? So the way this ends up working is that any particular node receives a purge, it's the closest one to whatever user is sending the purge, receives that and sends it out to all the other nodes. So this is more reliable in that, like, if there are net splits across the internet, it's not affecting all of the purges going to a particular area, and it also has the advantage of being lower latency generally. So So the problem ends up being that every server sends an acknowledgement to the sender server, which means that if we have 1,000 nodes, every purge results in 1,001, actually about 2,000 messages being sent out. And so essentially, like, each server ends up getting DOSed over time by all the other servers. So that's a pretty big problem. It also severely limits the scalability of it. All right, so after these two particular systems were built, our conclusion was this is hard. We should sit down and think about it for a while. And so that's what we did. So the second version of the system that I described there was actually built by me, and the third version that I'm about to describe was built by Bruce. And in my opinion, like the big thing that Bruce realized was that we were framing the problem in the wrong way. When I built the second system, I was looking at it as initially an atomic broadcast type system. And so I looked at all the different atomic broadcast algorithms out there and realized that none of these would actually work at the scale that we were trying to do it. None of them would work with the unreliability of the internet in general. And it was Bruce's great idea that what we were actually looking for was not atomic broadcast, but simply reliable broadcast, which is an important distinction. So the basic problem is we want to send a message to a set of servers. Applications of things like reliable broadcast, stock exchanges, control systems, yada, yada, yada. Man, speaker notes killing me. Then we have atomic broadcast, things like Paxos, Zookeeper, etc. And the thing about atomic broadcast is that it has guarantees that we don't actually need, that we don't actually care about. Specifically, the total order one there. We really don't care what order the purges get to each individual server in. And that was a key realization that we made. What we really want is a best effort type broadcast. We want to do the absolute best we can to deliver it, but if we can't deliver it, that doesn't mean that everything else should stop. So there's a bunch of different algorithms you can use to implement this. Sprinkler is a recent one. I believe that came out of Basho, actually. Plumtree, Scalable Reliable Multicast. And the one that we actually ended up going with was the bimodal multicast paper. So let's talk a little bit about how bimodal multicast works. So the goals of this are best ever delivery, predictable performance. And right, so there are two stages to this actual algorithm. There's the simple, like, I'm going to distribute this message as quickly as possible to all the places. And then there is the part that deals with loss in the system. So it's the anti-entropy or the gossip phase. Right, so the way that we actually ended up implementing this is simply just sending out a UDP message to every server in a for loop. Really stupid simple. Right, and so then the gossip phase kicks in occasionally. And what this ends up doing is it picks a random server out of all the other servers that every server knows about, and it sends it a digest. It sends it like, here are the things that I know about. Right? Let's walk through an example of how this actually ends up working in practice. So in this example, we have A, which has received 1, 2, and 3 as far as messages go. And we have B, which has received 1 and 2. And we have C, which has received 1 and 3. So during the gossip phase, each node ends up picking one at random, which in this case very conveniently was B picks C, C picks A, and A picks B. So each of them passes along, okay, here are the ones that I know about. And then the recover phase kicks in. So each node realizes, oh, I'm missing one, and will send a recover request to the other node that it just got the digest from. So there's 3 phases: broadcast, gossip, and recover. And let's see if this GIF is going to work. Nope, that's cool. So in this case, what this GIF was supposed to be doing at the moment was actually showing the way that the gossip phase will spread even under extremely high message loss. Basically, the end result is after about like 10 rotations of like picking servers at random, they've all gotten the message at that point, even though it's entirely random. For now, and Right. So this algorithm has a really interesting property in that when one server gets behind, none of the others actually care about it anymore, right? Each server ends up being responsible for its own destiny, for its own set of messages that it gets. So instead of having like a constant, hey, you need this hey, you need this message that you missed. Hey, you need this message you missed. Hey, each server then just goes, it's not my problem. If it needs a message, it'll request it from me. And so it has really excellent scalability properties. Also, we implemented retransmission limits in it, addressing the problem that we had with the second version of the system in which servers would DDoS each other. And here, so this is one of the graphs that are, one of the charts that are out of the paper itself. So this is actually kind of neat, so I'll take a second and explain it. We're looking at two different kinds of broadcast algorithms in this case. The ones that are falling down here are a traditional broadcast where every server is responsible for every other server, as opposed to being responsible only for itself. And so you see that as soon as the perturbation rate goes up, essentially like what the message loss is in that case, the scalability of the system drops dramatically. However, the paper refers to bimodal multicast as PBcast, and you can see that even so at an unperturbed host there at the top, even when it's a high perturbation rate on other nodes, it doesn't actually cause any problems, which is super important. So our conclusion is basically that best effort is basically okay. Even though it is technically possible for messages to be lost in a system like this, the neat thing about it is that we can tune exactly how many messages we would expect to lose. And in our case, we want that to be extremely, extremely few. And so we have a lot of gossip protocols going on. We do it frequently, and we make sure that the messages actually get around. So let's look at how this actually works in the wild. Well, actually, stepping back for a second, the actual development process for this system. Who here is familiar with Jepsen? Cool, a few people. Awesome. So Afer or Kyle Kingsbury developed this thing called Jepsen, which is used for testing distributed systems. The whole idea with Jepsen is that it will start sending messages into your distributed system, then cause a net split between them, and see how many actually get through, how many are lost, and how many are acknowledged but end up being lost anyway. And so we used Jepsen extensively while we were building this system, which means that in the end, when we actually deployed it, we've seen very, very few problems with net splits in actual production. So when we were testing this, we tested it on EC2. What we ended up doing is that Jepsen's really great for the development process, but for the testing process, when you're building distributed systems, you really want to put them through a torture test of sorts. And so we developed this thing called Avalanche, which extends Jepsen in order to let you do extremely long tests. So if you run tests on a particular distributed system for, say, 2 or 3 weeks, what Avalanche will do is occasionally it'll put random faults in the network. But it does it in a repeatable way. So when you go back in order to fix whatever problem that you have discovered, it'll actually, you can go and replay that exact series of events that led to the problem to start with. Super useful if you're developing distributed systems. I don't remember what I was going to say on this slide, but I stand by it. So let's look at the real world behavior. So here we're looking at the actual end-to-end latency across the world for messages received at a particular place. So at our New York pop, you see on average, it's the 95th percentile. The latency for the purges that it receives is about 42 milliseconds across the world. Tokyo is a little bit longer at 133 milliseconds, but still, the actual number of faults that we see that extend beyond that is way, way low because the system picks up the faults really quickly. Right. Okay. So there's a couple examples in here of shit going awry and how the system actually reacts to it in production, which I'm kind of excited about. So here we're looking at essentially a network misconfiguration that occurred in our system. So looking here, we have the actual throughput of messages over time, and then over that same time period, we have the latency with it. So in this particular case, what we're looking at is a small set of servers ended up being completely split off from another set of servers. So the end result of this ended up being that even though we were totally dropping messages to these places, they all got through. They were just slightly delayed. Right, so at another point, due to a provider of ours, we had a partition between New York City and London. And in this case, again, we have the throughput on the left, and on this time on the right, we have the number of recovered purges. And so here we see that, like, basically, although New York City and London were split off from each other, they could both contact other nodes in the system. And so they were causing each other to recover messages from other nodes. So point is, the messages still got through. And this is an example of packet loss as opposed to a full-on net split. So here we see the throughput of messages there bouncing between 200 and 300, and the number of recovered purges over here on the right bouncing up around 100. So even though we were losing messages, it just rapidly recovered them. And this is the final example. This is a particular node was under DDoS, which is, and so you can see like a really interesting thing occurs here where everything is totally fine, and then suddenly like the latency spikes up. So again, some messages were getting through, but it ended up recovering really rapidly. And the cool thing about this is that even when those, even during that time period, like we couldn't actually even log into that particular server. Like it was like totally cut off from the rest of the network. But it still managed to actually get some through via other servers. Right, so why do you care? Probably pretty unlikely that there are many people in the audience here who will actually need to go and implement reliable broadcast across the world. But the reason I'm up here talking is not because I want to sell you Fastly. That's not actually why I'm here. You know, although you should use Fastly, it'd be really great. But if you have something that works for you, then that's great. You should use that. I'm also not up here attempting to do a recruiting thing. Although if you wanted to come work Fastly, that would be all right with me. Whatever. So the point that I'm actually trying to make up here is that there are lots of times. God damn it! I really wish I had my notes. Okay, so there are lots of times when we're faced with a problem when we're building software, and there are lots of systems out there that almost kind of solve it. If all we have to do is like relax our like goals a little bit, then maybe NSQ would have solved this. I'm sure NSQ is a very good system. Probably wouldn't work all that well for this particular thing though. But we probably could have used it if we had like decided, okay, well, we'll just relax what we're looking for a little bit. But if the goals that you have in mind are actually important for you and important for your project and important for your company, I think it's a mistake to constantly be attempting to always use existing systems. If we're really full stack engineers, we should be willing to build something new rather than relying on the things that are out there. And I guess I'm saying this somewhat from a selfish thing because I'm just so tired of using software that almost kind of works. But so that's my point. If we're calling ourselves full stack engineers, let's not settle for what is actually just kind of close to what we're trying to do, but be willing to build and dig and make something better. So thank you. Questions? Right. So you asked what the actual what the protocol we're using between the nodes is. So we're using UDP for everything, and I probably should have covered this in the actual talk. But the reason we're using UDP instead of TCP is because we don't care about the order, and we also don't care about when things are lost. Right. The protocol. Right. Exactly. So the protocol bimodal multicast system is designed to do a lot of the same things that you would use TCP for in this case. So UDP works well enough. Right. Right. So garbage collection is indeed a somewhat hard problem in this particular case. The way that we went about solving that for the general case is by realizing that the message digest that we're sending around doesn't actually need to be a list. It could actually be a range. And so in the normal state of operation for this system, all we're actually sending around is a list that goes, I have 1 through 10 million. So instead of being like 10 million numbers, we have 2 numbers. Long term, so this is actually a really hard question. We're still debating about the right way to solve this long term. But essentially, we need some way of knowing that all the other servers have actually received something. And so building in a layer to do that wouldn't actually be all that hard. We just haven't done that yet. So I think it's somewhat easier than the original problem because this is entirely asynchronous. Like if something builds up for a long period of time, like we don't actually care. We only care about it once it reaches like some incredibly high threshold. But yeah, that is a problem. Right. So we don't yet, and that's an extension I've been really wanting to build for a while. So the way that the gossip protocol kicks in inside bimodal multicast is just it kicks in like once a second at the moment. However, what we could do is extend this to go, okay, well, let's actually kick this in every 50 milliseconds, but only for nodes within your data center, or every 200 milliseconds, but only for nodes within your region. And so in a lot of cases, I think that would actually like make it way faster to recover. So yeah, we're going to do that. Sorry, can you repeat that a little bit? I didn't totally follow. Mm-hmm. Yeah. Oh, sure. Okay. So this is that middle phase where we do the gossip protocol, right? And so essentially, like at that gossip protocol phase, every node picks another node at random and says, here are all the messages I know about. Like here's just a digest saying like I know 1 through 10 million from this server, 1 through 5 million from that server, and so on. And so when that net split heals, they start communicating back across. Those nodes on either side will quickly learn that they missed messages and then request them from other nodes. Any other questions? No, please. Right. Yeah, I'm glad you picked up on that. So the way it actually ends up working is that the message ID is not totally ordered. It is instead a tuple of the server ID, the timestamp of the start of that server, and the actual incrementing message ID. And so that's how we end up differentiating them. Right. Yeah, so we're definitely intending to open source various parts of it. Avalanche was the first start of that, but it is not entirely clear yet which individual bits will open source, but that's definitely something we're intending to do.
You guys released some real-time charting?
Yeah, we did that last week. Epic, yeah. Oh yeah, no. Oh no, the Epic is actually really cool. So we have this real-time dashboard when you first log into your Fastly account. And the problem is we started using D3 for this. However, we quickly realized we were eating an entire CPU core just for the graphs on this one page. And so what we ended up doing is building something that used a combination of D3 and Canvas to minimize the actual number of writes that were happening, like graphical writes happening on the screen at any 1 second. Canvas writes way faster than SVG. So we ended up releasing that as Epic, and it uses on our dashboard, it uses about 3% of a core on a like modern MacBook as opposed to 100. So pretty cool. Anything else? Thank you.
Thank you, Tyler. All right. 2 more announcements. One, beer is at Toad Hall tonight, if anyone would like to join. It's a couple of blocks away. I believe it's on Mercer between Worcester and West Broadway. And second announcement is from the Web Performance Meetup, we have Sergey Chernyshov, and he would like to make an announcement. Here he is.
Hi, guys. I just came here, and after a couple talks about incidents and stuff like that, I realized that you might be interested. This Wednesday, we have a talk by Alois Reitbauer talking about the dark arts of building production incident system. We usually talk about performance at Web Performance, New York Web Performance Meetup, right? But sometimes we also talk about scalability, and sometimes we also talk about operations, especially as they connect to performance. So this might be something you might be interested. So New York Web Performance Meetup this Wednesday. If you're interested, just look it up. Thank you.
All right. Thank you. And thanks, everyone, for coming out. Thank you to our speakers. One more round of applause for them. Thank you to Squarespace for hosting, and we'll get out of your hair. And anyone who would like to join, I think a bunch of us are going to head over to Toad Hall. So thanks again.
Yeah, man. I know you think well. Huh? Me too. I was like a one spot. Oh, yeah? That's cool. What do you do? Web producer by trade and internet radio producer. Okay. Oh, yeah. So you been having any events like hackathons come up? Or any stuff?
We may. I don't know what the schedule looks like for the summer yet. We actually just started talking about it. So I don't know. If you want to kind of off. I don't have a card.
You're on LinkedIn?
I am.
It'll select me on there. It'll be mailing list.
That's great. Okay, sure. We'll do.
And you guys hire you as well? Cool, I'll send you a resume.
Okay, please do.
It's web produced by trade and also tech background.
Okay.
CMS.
Oh, please do. I appreciate it. Nice meeting you. John. All right. Good to meet you.